This is basically a lens and image problem, okay? But it's a lens and a camera that makes an image on a piece of film. And here's what's happening. We've got the Golden Gate Bridge out here. Okay, so here's my Golden Gate Bridge. And we have a lens in a camera. And it's making an image of the Golden Gate Bridge, okay, on a piece of film. Okay, so here's my distance to the bridge, S. Here's my distance to the film, S prime. And instead of using the image height, I can use the image width, okay? Because you could just take this whole thing and think about it sideways. This lens is circular, so it doesn't make any difference what axis we use. So I'll take the width of the bridge and call that the height. The width of the image of the bridge is H prime. Okay, now we're told this, that initially the photographer starts with a focal length of 50 millimeters, and that bridge picture entirely fills his 36 millimeter wide film. So that tells us that the focal length of the lens is 50 millimeters, and H prime, the width of the image, is 36 millimeters. Okay, that's what we're told. We can say a couple of other things as well. Look, the focal length is 50 millimeters. How far is he back from the Golden Gate Bridge? Oh, let's say an awful lot more than 50 millimeters. And so this distance here, S, we can assume that's approximately infinity. Okay, in terms of this problem, it's not going to make any difference. And our basic relationship, our basic thin lens relationship, 1 over S plus 1 over S prime equals 1 over F. If we assume that S is equal to infinity, this term right here basically goes to 0. And so as a consequence, our relationship reduces to this. 1 over S prime is equal to 1 over F. And so S prime equals F. And this tells us that the image basically forms right at the focal point. And so this distance S prime is equal to F. It's just equal to the focal point of the lens. Now, we can also think about the magnification. Magnification is equal to the height of the image divided by the height of the object, okay? But that's equal to negative S prime over S. Now, I'm going to rewrite this relationship this way, okay? I'm going to write it as H prime over S prime is equal to negative H over S, okay? Now, this is the actual width of the bridge, H. S is the distance of the person from the bridge. And so this whole fraction doesn't change. This is constant in the problem. Okay, this doesn't change. So what that tells me is this: no matter what camera the person is using, the ratio of H prime to S prime stays the same. Okay, so H prime is basically proportional to S prime. If I double this because the ratio of the two has to stay the same. But S prime, we know, is equal to F, so that tells me this: the height of the image is just proportional to the focal length. If I double the focal length, I double the height of the image, or in this case, the width of the image. So let's use this piece of information with the data that were given in the problem. And from here, we can solve. And the solution is actually quite straightforward. It's a ratio reasoning problem. Initially, I have a focal length of 50 millimeters. And I end up with an image height of 36 millimeters. Okay? Ultimately, I'm looking for the image to completely fill the 12 millimeter wide CCD detector. And so I want an image height of 12 millimeters. Now this has been reduced by a factor of 3. The new image height is 1/3 of what it was previously. But since H prime is proportional to F, what that means is the new focal length to make this happen has got to be reduced by 1/3 as well. 1/3 of the image height requires a focal length that's 1/3 as big. And so I need to have a new focal length of 17 millimeters. Okay? And so I can solve this just by thinking about ratios. These two are proportional to each other. So if I reduce this one by a factor of 3, I must reduce this one by a factor of 3. And that's the most straightforward way to solve this problem. Here's my assessment. The focal length of the lens basically is how far the lens sticks out from the front of the camera. You can think about it that way because it's got to. And digital cameras have smaller detectors than the old film, and we know the lenses don't stick out as far in front of the camera, so we expect to have a focal length that's smaller. So this matches our expectations of how the world works.